Okay, so I just want to show you a little equivalency here. Um, so let's just continue with fields, and specifically gravity fields. And we talked about the fact that gravity fields are measured in the unit of newtons per kilogram. In other words, you know, around a particular, say, large object, such as a planet, okay, if you happen to be, somewhere near the surface, you're going to describe the strength of the gravity field in terms of how many newtons of force are experienced by some mass, generally near the surface, right? So for Earth, this is Earth, and you are a person near Earth. In fact, you're standing on Earth. Okay, we want to know how many newtons for every kilogram on your body you feel, and we know it's about 9.81 meters per second squared, which, remember, is the exact same unit as newtons per kilogram. Let's make sure we put the right units in. Okay, these are equivalent measurements. Okay, and we went over that last time. So we have this way of talking about this acceleration slash field strength, and the symbol that we use to describe it is little g. We say little g is 9.81 meters per second squared. How does little g tie into Newton's universal gravitational law? So we also learned that the force of gravity is equal to big G, gravitational constant, times the two masses all over the distance squared. So sometimes it's confusing, like what we're talking about when we say r squared. I think probably the best way to explain that is first of all to describe the concept of center of gravity. Did we talk about center of gravity? We did? So who can tell me what center of gravity means? What's the center of gravity? Say for a sphere like Earth. What does that mean? Yes? Right. So if we imagine that this is a three-dimensional object, it's a little hard to do, so I'll put the traditional sign so you'll know it's 3D, right? The shiny curved window symbol. So this is a sphere, and if we were to look at every line of force, we would find one intersection point in the center of this object, and Newton said it is if all of the mass of this object is concentrated at its center. Okay? So if we look at this situation here, right? If this is Earth, we just erase this little e. If this is the Earth here, okay, so this is Earth, and we look at this formula, we could call this big M, right? This is the center of mass of Earth, right? And then over here, some object, in this case you, also has a center of mass. On a person, that tends to be at their belly button, or around their belly button. Okay? So if you have all the lines of force for your gravitational field, they would intersect at your belly button. The distance between your center of gravity and the planet or object's center of gravity would be r. It's essentially a radius, right? It's the radius of these two objects. So when we were learning Newton's law, general law, we tend to think of it as, star maybe, like the sun, and Earth out here, and we talk about this as the distance between them. But you can also apply it to a situation where an object is standing on the surface of a planet. So there's two ways to talk about weight, right? One more thing that we better remind ourselves is our classic F equals ma, so Newton's second law. And up until now, we've described this situation, the downward force towards the center of the planet, we've called that what? It's the name for the force that is felt by an object near the surface of Earth. What do we call that? The downward pull of gravity on you. Measured in units. Yeah, weight. Good, weight. So F equals ma near the surface of Earth translates into, instead of saying F, we say it's a special kind of force. It's a weight force. This m is the mass of the object, or the little m that we were talking about over here. and the acceleration is the special acceleration called g. So weight equals mg. Okay? Can we not say the force of gravity on this person can be calculated in either way? We can either calculate the force that this person will feel as Fg equals gmm over r squared, or as weight equals m times g at the surface of the planet, because we know what g is here, right? If we know what g is, we can make these two equations equal to one another. So what we'll get from here is we'll get this. We can say weight and the force of gravity are equal, right? They're the same thing. So weight is mg. We should be able to say that mg is equal to big G, big M, that's the mass of the planet Earth, over little m, all over r squared, are equal to one another. Okay? Now notice what we have here. The small m crosses off. So what does that mean? That means near the surface of a planet, in a gravity field, the mass of the object becomes irrelevant when you're talking about its acceleration. Okay? This was noticed by who way back when, that the mass does not matter when we're talking about the acceleration of an object near the surface of Earth. Galileo. Good. Galileo. So what we can do is we can say, now that Newton's come on the scene and come up with his laws and his law of universal gravitation, he's taking Galileo's idea and mathematically provided support for it. Okay? So Galileo did it with just experiments. I see it. This is what happens. Newton provided some of the background theory, right? Sometimes science works that way. Here's scientific observations. How do we apply math to it? And sometimes it works the opposite way. Here's our theory. Now can we go improve it, right? Which way do you think it works more often? I don't know. I'm just asking you. I'm not sure if there's an answer to that. But observation, then theory versus theory, then observation. I think probably historically that's more likely the way it would have gone. But now that you're pushing frontiers and it's becoming harder to create the technology to find these things, I think it maybe is now more theory driven, and then we build machines to try to prove the theory right or wrong, or experiment on the theory. Something that leaps to mind is like the Higgs boson, right? Which was theorized 50 years ago, and then it wasn't until very recently that a machine was made that could actually experiment with that. But I'm digressing. So what we get out of this is we get a formula that we can use to predict G on a planet that we already know the mass of, or if we know the acceleration due to gravity, maybe we can then figure out the mass of the planet itself, all right? So this is a handy little formula that gives you some interesting information. Should we try this for the Earth and see if it does work out to give us the proper value for G? Why not? Okay, so we just have to look up a little tiny bit of information. What is the unit for big G? You can see, is it a big number or a small number? Mm-hmm. Is that right? And what units is it in? Okay. Can someone find me the mass of the Earth? I'll put a subscript to say we're talking about the planet Earth right now. It's 10 to the 24 kgs. And you probably have the radius of Earth handy there as well too, do you not? If you don't, we can go find it. Six times 10 to the 6 meters, I believe is right, or close to that. So 6,000 kilometers is the radius of Earth, right? So add another exponent there, so 6 times 10 to the 3 km, 3 more, 6 times 10 to the 6 meters, right? Can someone pull out their trusty TI-83 and solve this for us? We'll wait. Right. So calculating this out with the current number of sig figs that we have here, which, by the way, you can look up and have many more sig figs than we do, but with the number that we have, we get roughly about a value of something like 10.0 meters per second squared. So, pretty. Some people are getting 9.73. I'm not sure why we're getting different values. Are we all using the same calculator? Well, apparently I'm not supposed to trust your answer. So if you average these out, you probably get what you want, right? Or roughly what we take for granted to be the acceleration due to gravity. By the way, 10 is a nice approximation. So if you ever have to do math in your head and you just use 10 for g, you can get a long way with that. Okay, are there any other questions about that? Okay, well, while we're at it, why don't we look at some other interesting and neat things that we can do? Let's talk about planetary orbits, or just orbits in general. So planetary orbits or orbits in general. So we're all, I hope, aware of the fact that our solar system has at its center a bright star, and there's lots of planets orbiting around. And we know, or we've heard probably, that those planets follow elliptical orbits, which is true. However, those ellipses are very close to being perfect circles. Okay? It's not really an egg shape like you sometimes see people putting, right? So it's not really like a, like a giant egg like this. Okay? There are some things with orbits like that. For instance, comets have orbits more like this egg. Oh, you guys can't see the egg. All right, let's fix that. I think I can change its color there. So this might be like the orbit of something like a comet, but planetary orbits are very close, although not perfectly circular. Okay, they have a very quite low eccentricity, which means how far from being a perfect circle they are, how oval or elliptical they are. Do you guys still do conics in math? Like looking at a cone and seeing how you can get a hyperbola out of it and an ellipse and so on. Do you do conic sections? Oh, that's unfortunate. Anyway, an ellipse is one of the conic sections. But if you don't do that, then I'm not going to waste my time talking about that. So, oh dear, do that. So if we look at this scenario, we can essentially approximate Earth's radius as being a perfect circle, or what we could say is we could call this the average, if you want. The average radius around the center star. Okay. Now the force between these two things, between these two massive objects, is going to be found with your universal law of gravitation. But a little while back, we also covered centripetal force, did we not? And in this case, we have an object moving in a circle, that's the planet, and if it's Earth, it's Earth, if it's, Jupiter, it's Jupiter, and they essentially more or less move in a circle. What is it that is preventing then the Earth from just zipping off into space, right? Because if you imagine that there's a tether here, okay, it makes sense as to why it moves in a circle, but what is providing that tethering? And it's obviously got to be the force of gravity. So what we can say then is we can say the centripetal force needed to make a planet go in a circle is provided by gravity. We had a couple of different ways of indicating a centripetal force, did we not? Do you remember what they are? We represented centripetal force like this. Can someone tell me how we did it? No, you can't? What? Well, don't worry, I'll remember for you. mv squared over r, right? And we also broke it down to be in terms of the circumference of the circle in a period of time, and that worked out to be m 4 pi squared r all over t squared. Do you remember that formula? Are you just saying that, or do you actually remember? So for orbital mechanics then, if we want to talk about a circular orbit, what we can do is we can make some things equal to some other things, right? We can make centripetal force now equal to the force of gravity. We could say, for an orbital system, we could say mv squared, little m, right, is representing the object that's doing the orbiting. mv squared over r is also equal to m 4 pi squared r all over t squared. And that can be made equal to Newton's law of universal gravitation, which is big, well, G, big M, little m, all over r squared. What do you notice appearing in the top of all of these equations? The mass of the orbiting object. Okay? So the little object, in this case a planet, or it could be a satellite, or whatever, is allowed to be crossed off, right? Divide out m from the top of each, and you get a useful set of equations to talk about orbital mechanics. So if you know certain things about orbiting objects, you can figure out certain other things about, say you're looking at Jupiter, for instance, and you're interested in figuring out what the mass of Jupiter is, right? It's pretty hard to go and weigh Jupiter, obviously, or to go to the planet and perform experiments to try to sort out its mass. But Jupiter has moons, right? So if you know, say, the velocity of Jupiter's moon and the orbit of Jupiter's moon's radius, the radius of Jupiter's moon's orbit, am I saying the words right? Are the words coming out right? You might be able to figure out something like the mass of the actual planet. So let's try that. Let's say that you know with a telescope and you've looked up at one of the moons of Jupiter. Can you pick one? Can someone pick a moon of Jupiter for me? Go on your smartphone. Ganymede. Find me Ganymede's orbital radius, because you can probably figure that out with a telescope, I think, probably somewhat easily. And then find me the period of Ganymede's orbit. And what we want to get from that is we want to know what is the mass of the planet Jupiter, just using information that we might be able to get from a telescope. So let me just rewrite this formula, leaving the mass of Ganymede itself off, which is the little m. So what we'll end up with is 4 pi squared r over t squared. We'll do some fun algebra here. And what we want to do is we want to isolate for m. This is the mass, and I'll put a j there, little j, mass of Jupiter. So let's go with a mj. Let's try to do some mental, so we should get 4 pi squared r cubed gt squared. Is my algebra good? Check my algebra. Cubed, right, r comes up here, divide off g. Yeah, I think we're good. And can you find me some values that we might be able to get, say, off the web? 4 pi squared, what is the radius of Ganymede's orbit around Jupiter? No, I can't use miles. 1.07 times 10 to the 6 kilometers? Yeah, that's what it is. Okay, so we gotta, so this is in kilometers, so we gotta have our units in meters. So we gotta jack that up to 9, right? Okay. Okay. And we cube it. G, 6.67 times 10 to the negative 11. I'm just going to leave the units off. Let's put the units on. I always forget what they are, though. Um, meter cube per kilogram per second squared. Okay, and the period of Ganymede's orbit in seconds, or whatever you can find. Can you just Google period of Ganymede's orbit? We'll give it to you. 7 days is what it tells you. Okay, so 172 hours times 3,600 seconds in every hour. So boom, boom, that should give us seconds down there. Okay, so math time. We'll just pause and math it. Yeah, sorry, we forgot that this is squared. Make sure that that's squared. So we're just noticing that our seconds aren't going to cross off, right? All we should be left in is kilograms, right? So seconds cross off on the bottom. Meters cubed here, under meters cubed, that crosses off, right? So cube meters, and then kilograms to the -1 on the bottom means kilograms on the top, so our unit should be correct. So there's our check, just to kind of make sure that we're in the right ballpark here. So working this out, if we do our math right, my calculator tells me 1.89 times 10 to the 27 kilograms. And we'll Google it. I know, but I just want to make sure. Oh yeah, there it is. Except it's not in my little window. Bring it over. So there it is, according to the Googs. So I'm not sure if that's the exact method that you would use to find this if you were a scientist, but it is a method that works and gives you pretty good results. Okay? So we'll stop there.